Good evening to all. Today we are going to discuss about most important thermodynamic process, that is isentropic process, which is also called adiabatic process. And this isentropic process used for the real gas applications. So I'm sure this video is going to be very interesting. So please do keep watching until then, and please subscribe my channel and don't forget to hit the bell icon. Thank you. So let's begin the discussion about thermodynamic process, that is isentropic process for real gas application. Before that, let's understand thermodynamic system. So if you see thermodynamic system, so what do you understand? Like compressor does work on the gas, so energy of gas increases, and high pressure energy of the gas when there is expansion and power is generated using the turbine. So the energy level decreases. So we are focusing only on the gas. That means if you see thermodynamic system, that means our intention or attention is only the gas, not the compressor, not the turbine. So with that focal point or with that consideration, let's say there is a sign convention. So if heat is transferred or heat is added to the gas, that means heat is added to the system. Thermodynamic system is considered positive when heat is removed from the system. That means heat is removed from the gas, it is negative. When work is done by the gas, that means using turbine, work is done, which is considered positive. When work is done on the system, yeah, that is on the gas by the compressor, it is negative. When the energy level of the system increases, that means energy level of the gas increases, it is considered positive. When energy level of the gas or when energy level of the system decreases, it is considered negative. This is as per the sign convention for a thermodynamic system. Now, types of system, it is open system, closed system, and isolated system. In case of open system, you can see there is a flow of the mass flow occurs and as well as energy transfer occurs. In case of closed system, there is no mass transfer, but energy transfer occurs. In case of isolated system, neither mass transfer occurs nor the energy transfers. And real gas equation, P v is equal to Z N R U T. So on further simplification, we can write P small v is equal to Z R T, which is the most important equation for real gas application or real gas equation, which can be used for derivation for other parameter, other like work transfer and other parameter like heat transfer, energy transfer can be used using this equation, where P is equal to Z R T. Z is the equal to which is considered compensating factors. Now work transfer can be shown on PV diagram for closed system. This is for open system. Area under the curve on the x-axis on PV diagram. For the closed system, A is equal to work transfer. So and by the formula, work transfer for the closed system is integration of PdV. Similarly, work transfer for the open system, area under the curve on y-axis is equal to, by the formula, is minus integration VdP is same. Use this equation and this both are same. And work done by the system, this is as per sign convention, is positive. Work done on the system is negative. This is as per sign convention. And work transfer per unit mass is called work head or head. Now energy transfer equal transfer for the closed system is equal to change of internal energy, and change of internal energy is written as integration of CVDT. So energy transfer for the closed system can be written is integration of CVDT. Now energy transfer for the open system is equal to enthalpy change, and enthalpy change is defined as integration of CPDT. So we can write energy transfer for the open system is equal to integration of CPDT. And as per sign convention, energy of the system, if increases, it is positive; when decreases, it is a negative. Now, as per the first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer. So Q is equal to W plus E. But the most important assumption is that the efficiency of thermodynamic machine is 100%. That means there is no losses considered during the transfer of work, energy, and heat. With that assumption, first law of thermodynamics, heat is equal to work transfer plus energy transfer. Now isentropic process shown on the PV diagram, TS diagram, you can see the PV diagram. When there is expansion in this process, pressure decreases, volume increases. When there is a compression, you can see volume decreases, pressure increases. In this TS diagram, you can say this is compressor, this is compression process, this is expansion process. And the most important part is there is no change of entropy. You can see here. So entropy remains constant in the isentropic process, and this isentropic process is also called adiabatic process. But so since there is no change of entropy, so work transfer is equal to energy transfer as heat transfer is zero. There is no heat transfer, so no entropy change. So work transfer is equal to energy transfer for isentropic process. Now let's derive the isentropic process for the work transfer. You can see in the PV diagram, area under the curve on x-axis will show the work transfer, and entropy remains constant. So you can use the very important equation, that is PV to the power k. K is a Cp by Cv, is equal to constant. This is equation for isentropic process. So P can be written like this: P1 B1 K, P C is equal to C is equal to P2 V2 K, which can also written V2 by V1 equal to P2 by P1 to the power 1 by K. Okay, you can say P2 by P1 is equal to V2, P2 by P1, you have to set minus, because V2 by V1 is P1 by P2. Sorry, yes. So this is minus. Now real gas equation PV is equal to Z RT P1 B1 Z1 RT1 P2 V2 Z2 RT2, and K is equal to Cp by Cv. So now let's derive the equation. W is equal to integration PdV, and just replacing P, we can write C V to the power K minus K. Actually C has gone up, so minus K and dV. So further we can after integration, finally we can derive in this form. W is equal to Z1 R K minus 1 bracket T1 1 minus P2 by P1 to the power K minus 1 upon K. So this is a work transfer per unit mass, and for total heat transfer we can just multiply M, you will get the total heat transfer, total work transfer. So work transfer per unit mass is this, and total work transfer just multiply with mass M with this, it will give the total. Now energy transfer is CVdT for the closed system. So we can write energy transfer per unit mass is CV T2 minus T1, and total energy transfer just multiply with the mass M CV T2 minus T2. T2 minus T1. So heat transfer, as per first law of thermodynamics, you have to add Q is equal to this plus this. Both you have to add. So this is heat transfer, and total heat transfer just multiply with mass M. But you will see in this process, this becomes zero. In the isentropic process, you can see TS diagram, area under the curve on x-axis 0. That means when this all value is put, it becomes 0. So heat transfer is 0 on isentropic process or adiabatic process. Now isentropic process in open system, same thing we can write now minus BDP with integration, and after replacing all the value, we can finally come to this equation, and W is equal to Z1 R K upon K minus 1 bracket close T1 into 1 minus P2 by P1 to the power K minus 1 upon K. This is the work transfer per unit mass. For total work transfer, just multiply with mass M. You can see on PV diagram, area under the curve on y-axis will show the work transfer on open system. Energy transfer for the open system CPdT. So we can write Cp T2 minus T1. Just total energy just multiply with mass M. And as per first law of thermodynamics, Q is equal to this plus this both. So this is heat transfer, and total heat transfer multiply with this. So this is again TS diagram. You will see heat transfer, area under the curve is 0. So heat transfer in this case also is 0 for isentropic process. Now let's understand with example. Nitrogen gas has initial pressure and temperature are 0.5 bar gauge and 30 degrees Celsius respectively. Gas is compressed such that final pressure reaches to 0.6 bar gauge on constant entropy process with consideration of real gas. Calculate work, energy transfer, heat transfer during this process for considering closed and open system. Also calculate the inlet and outlet specific volume Following data are given: mole weight of nitrogen, universal gas constant, specific capacity at constant volume and constant pressure is given 20.881 and 29.187 respectively. Compressive factor at inlet and final condition same, that is 0.999, and local barometric pressure is 1 bar absolute. Now for the closed isentropic process, for the closed system, all data are given and P1 is converted 1.5, P2 is 1.6, small weight Z1, Z2, CP, CB or RU are given. Now let's calculate the gas constant RU by M. Then CPCV is also converted by dividing by mole weight multiple 1000 for this unit. Then CP by CV is calculated. Then V1 is calculated, V2 is calculated. Then isentropic outlet temperature is also calculated. The work transfer is calculated using which is coming minus 4191, and energy transfer is also same 4001. This is minus, this is plus. So heat transfer, if you add these two, it becomes zero. So in case of closed system, you can see there is a work transfer minus 4191, energy transfer plus, that is 4191. If we add these two, so heat transfer is zero. In case of open system, work transfer is minus 5858 and energy transfer is 5857, which is plus, this is minus, this is plus. Again, the energy total heat transfer is zero because plus and minus, if you add these two, since this is calculated using Excel file, so you can see it is closer to maybe zero. Less than 0.5 is considered zero. So it is very closer to zero, you can say. So I hope you have enjoyed this session. Thank you. Thank you for watching.